So, I'm doing science education. We're doing some science educationing about a topic that has been suggested by a longtime fan of the show, longtime viewer, friend of the show, Dave. Dave suggested that I answer one of the burning questions of humanity, one of the true scientific queries plaguing us since the dawn of time, one of the oldest questions in human history. Why sky blue? Why sky blue? Thanks, Dave, for that good question. Let's get right into it. So before we answer the question of why sky blue, we have to we have to do a couple clarifying things, learn some stuff beforehand so we get all the information we need. So let's start with some of the basic things we need to know, and that's what is blue and what is the sky. I think we all know what the sky is. I hope we all know what the sky is. And if you don't know what that is, then you should probably go outside. Turn off this video, look outside, look up. That's the sky. But what is blue? That's a very good question, I think. That's a very, very nice question to start with when we're trying to answer why the sky is that. And what is blue? What is color? And the answer to that is that color is light. To which you'll go, what is light? Baby, don't hurt me. And why are those two the same thing? And the answer to that is that light is everything. It's how we see things. Light is how we know that anything's around us, how we know what colors things are, and also how we talk to each other. Except when we're actually doing like this kind of talking where I'm making sounds with my mouth, that's not light. That's actually, that's sound. That's nothing to do with light. Color and light. Color is just different wavelengths of light because light is a wave. And you'll be like, what is a wave? What is a wavelength? Light is a wave. And that means that light goes like this, and has all those like big humps and valleys and peaks and valleys. Waves have a couple little fun little things that they have. Primarily, they have wavelengths, and that is not the length of the wave, which I might be the only person who's ever thought of it that way. It's not the length of the hump, it is the length between the humps. That is the wavelength, kind of the length of one cycle, I'll put a diagram. Light can have different wavelengths and still be like the same light. It's just different kinds of light, different colors. Different wavelengths determine color, and we have an entire spectrum of wavelengths. And at one end of the wavelength spectrum, electromagnetic spectrum is what it's actually called, we have what we call the short end. I don't know what I was going to say, like what we call one specific thing, because it's actually a lot of different things. But for example, we have at the short end, gamma rays, X-rays, ultraviolet, the short stuff, high energy, violet, blue. And at the other end, on the other side of the stuff, we have the long wavelengths. We have red, we have infrared, which is longer than red. We have microwave, we have radio waves. Radio is light. Radio is made of light. Not your actual radio, but the stuff that it's interpreting is light. And that's the spectrum, that's the electromagnetic spectrum, is those two very far ends and everything in between, in different kind of lengths and wavelengths of light. And we can only see one part of that spectrum. We can only see with our human eyes the visible part of the spectrum. That's why we call it that. And that's all the colors that you know. That's all the fun ones. That's the rainbow, the blues, the reds, the yellows, the greens, the purples too. Can't forget them. That's the only part of the light spectrum that we can actually see. We can't see the gamma rays, we can't see the X-rays, we can't see the radio waves. If you can, that's pretty cool, but you can't. But the sky is going to be one of those colors that we can see with our eyes, because we're going to see the closest thing that we can. So why is it blue? And why isn't it red? Or why isn't it yellow or purple or green? Why don't we have a green sky? Like, probably kind of gross, actually. I don't think that'd be very fun. Why do we have a blue sky? Well, that comes to a phenomenon known as something, that's for sure. It sure is known. Rayleigh? I don't actually know how to pronounce it. Rayleigh. It's Rayleigh pronounced that way. Rayleigh scattering. Rayleigh scattering is a phenomenon where when light hits a little particle, like we have in the atmosphere, like little gas particles, it scatters. That's what light does. The processes behind that do get fairly complicated, and quantum mechanics, and I don't think quantum mechanics is real. I can't say that, actually. This is science education. Quantum mechanics is real. Eat shit, Einstein. But the process of why light scatters and how that works is a bit weird. It gets a tiny bit complicated, and I think it's outside the scope of this video. But light scatters, and Rayleigh scattering says that when light interacts with a particle that is much smaller than the wavelength of light, remember those wavelengths? If you have a particle that's much smaller than that, the light scatters more. And the way and how much light scatters is actually a kind of, it depends on the wavelength of the light. And it is what we call a inverse relationship. So the shorter the wavelength, the stronger the scattering. The longer the wavelength, the less it's scattered. So why does our atmosphere have the blue? Well, if we think about it like this, we have the sun, and then we have us, and then the sun is above us, and there's the atmosphere between us. It's high noon. And when that happens, the sun is coming right down towards us. The light is going pew, pew, pew right towards our faces. Don't look up at the sun. And when the sun hits the atmosphere, the sunlight, not the sun, the sunlight hits the atmosphere, those red light particles going boom, 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 not getting scattered super much, super a lot. They're not getting super, super scattered because they're kind of long wavelengths compared to the other stuff. They're the longest of the visible wavelengths. So they're not getting super, super scattered. They're just kind of going boop, 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 and they get through the atmosphere pretty quick and then hit us in the face. And that's why if you look up, the sun is red. Do not look at the sun directly. Please don't do that. I'm telling you explicitly not to do that. However, let's think about the blue light. It's getting scattered a whole lot. When it hits one of those molecules in the sky, it goes and bounces off, and then it hits another particle and goes, and basically it just bounces all across the sky. And if you think of one little blue photon, it's going to hit an atmosphere thing, hit an atmosphere. I have a degree in this. It's going to hit a particle in the atmosphere, and it's going to bounce off really fast, and it's going to hit another one, bounce, 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 bounce. When it eventually bounces towards you, or makes its way towards you, your face, it's scattered so much it looks like it's coming from way over here. But the red ones is coming from directly above. And if you think of all the photons from the sun coming, all those bluish, greenish, the shorter wavelength ones are getting scattered a ton. They're bouncing around, bouncing around, bouncing around. So to you, it looks like there's just blue coming at you from everywhere. It looks like the entire sky is just radiating blue because blue is bouncing off of everything and they're just like bouncing around the sky and coming towards you eventually. And that's why it looks like the sky is blue. You just learned that. That's why the sky is blue. Rayleigh scattering, blue scatters more, red scatters less. But then you might go, haha, checkmate, I win. I have an example where the sky is in blue on this planet, not on Mars or another planet. What about the sunset, the sunrise, those weird times of day when the sky is not blue? There's reds, there's yellows, there's purples, there's greens, there's not greens. There's, there's those long wavelengths that you're talking about. Why are those up there? Why are those in the sky? To which I say, good question, and I'm going to answer it. So let's say it's like sunset, right? We all love the sunset. We all love it. It's a great time of day. Lots of pretty colors. And also it's almost nighttime, time to go to sleep time. So the sun at noon was shooting its light directly down through that little layer of atmosphere. Like, here's the sunlight, here's the atmosphere, here's you. But at, what did I say? Sunset? Yeah, sunset, it has to go through way more atmosphere to get to you because it's going through like the atmosphere at an angle, not straight down. So it's going through way more atmosphere. So as it gets closer to like just going through as the maximum amount of atmosphere it's going to be going through, it actually scatters so much that all that blue light would be getting scattered and then coming towards you eventually is getting scattered just away from you. It scatters too much. It scatters so much that it's not reaching you as much, which is why the sky gets kind of darkish. That blue light isn't coming through as much. It's getting scattered away. And that light that you would usually get barely scattered, that red, the yellow, the oranges, it's actually getting a bit scattered, and still managed to make it to you. So that's why you see all those brilliant reds and all that kind of smeared out, scattered across the sky, because they're actually having more chance to scatter throughout the longer journey to get to you through the atmosphere. And the blues are just getting scattered away to be the blue sky on some other person's face at that time. And that's why the sunset is red and yellow and all that fun stuff, and the sky is getting less and less blue. That's why the sky is blue in the daytime. That's why the sky is blue. Sky blue. I feel like I missed something. Oh well. Thanks for watching. Hope you learned.